Hello, this is Umesh Thamija, a chemistry expert from online chemistry classes. This is a video online chemistry class on electrochemistry for engineering and medical entrance examination. This will also be useful for your board examination. For more videos, subscribe my channel. You will be getting more videos on chemistry. Don't forget it, and watch this video completely, understand the topic. Wish you all the best. Happy learning. I'm sharing my screen with you. Can you see my screen?
Yeah.
Okay. So today's topic is specific conductance. Last time also we discussed the same topic, right?
Yeah.
Okay.
At the end.
Yeah, at the end, right? I will revise this one and then we'll proceed ahead.
Okay.
Specific conductance, right? The specific conductance is, we are explaining like this, that resistance is directly proportional to the length of the conductor and inversely proportional to area of the conductor. Last time we discussed this, right?
Yeah.
And resistance is equal to resistivity into R upon A. And this resistivity is equal to R into A upon L. Right?
Right.
Now if we make its inverse of resistivity is called as a conductivity. And we denote it by a symbol kappa. This symbol is called as a kappa. Is equal to 1 upon R into L upon A. Right? Inverse of the resistivity. So kappa is equal to conductance, because 1 upon R is called as a conductance. And L upon A is called as a cell constant. Right? Are you getting me?
Yeah.
So this is the specific conductance now. This is just mathematical formula that we have derived. And now I'll tell you what is its physical meaning. Suppose we have a beaker and these are the two electrodes, and I have connected it with a battery, and inside this we have electrolyte. Means here we have an electrolytic ions are there. We have A positive, we have B negative, right?
Okay.
And these ions move towards oppositely charged electrodes. The positive ion move towards the negative and negative ion move towards the positive. Now,
okay.
How fast or how easily they move, that is called as its conductance, right? The distance between two electrodes is 1 centimeter. Here I have chosen, and the length and the breadth is also 1 centimeter. So we can say area is equal to 1 square centimeter.
Okay.
And in this 1 cubic centimeter, the conductance is due to a certain number of ions here, right?
Yeah.
So we define specific conductance as conductance due to all ions present between two electrodes separated by 1 centimeter and area of cross section is so large that whole of the solution, is contained between the two. Between the two. Right? Getting it?
So you're saying the entire solution is between the two ions because of all the conductance.
Yeah.
Okay.
So this is how we define the specific conductances, right? And
Okay.
the units for the conductance. Now I'll talk about the units here. Unit is Siemen meter inverse. S stands for Siemen meter inverse. Or
Sir, can you speak up a little bit?
yeah, Siemen centimeter inverse. Units are Siemen meter inverse or Siemen centimeter inverse. Right?
Okay.
In CGS unit, it is a Siemen centimeter inverse, and this is the SI unit.
Okay.
Right? So we have now this formula, that is kappa is equal to 1 upon R into L upon A. Based upon this, we will be solving some numericals. Right?
Right.
And before that I'll be discussing here another topic that is called as the molar conductivity. That is called as a molar conductivity. Right?
Right.
I am writing this definition first. It is conductance due to all ions present between two electrodes all ions of 1 mole of electrolyte. 1 mole of electrolyte.
Okay.
Present between two electrodes separated by 1 centimeter, and area of cross section is so large that whole of the solution is contained between the two. Right?
The two electrodes?
Two electrodes, yes.
Okay.
But the point here is very important here. Where is it? All ions of 1 mole of electrolyte. In the previous case, when we talked about the specific conductance, we have not fixed any amount of the reactant. Here we are fixing how much? 1 mole of electrolyte. Right?
Right.
So suppose we say we have a 1 cubic centimeter and these are 2 electrodes. The distance between 2 electrodes is 1 centimeter and area is also 1 square centimeter. In that case, this molar conductivity or molar conductance lambda m will be equal to specific conductance, because we have defined the conductance in 1 cubic centimeter is specific conductance, right?
Yeah.
But in case our electrolyte does not fit into 1 cubic centimeter, then what we do, we keep the distance between the 2 electrodes same, but we increase the surface area. You can see distance is 1 centimeter and area of cross section is so large, we increase the surface area so large that whole of the solution is contained between the two. It means we have to multiply here with the volume V. So kappa into V.
Okay.
Right. So molarity is equal to, we know that number of moles upon volume. Right. Volume in milliliter, then multiply by 1000. Right.
Yeah.
You know this formula?
Is this molarity or?
Yeah, molarity formula, you know?
Yeah, I know that, yeah.
Okay. So N is equal to 1 here. So we can say volume is equal to 1000 upon molarity. So kappa into volume upon molarity, 1000 upon molarity is lambda m value. Tell me it out.
Okay. And kappa is conductivity and m is molar mass.
Yeah.
Okay.
N it out.
No. Hello?
Yeah. N it out here.
Yeah. No.
Okay. So unit will be Siemen meter square mole to the power -1. This is the SI unit. In CGS unit it is a Siemen centimeter square mole to the power -1. It is a CGS unit. 2 units, you know?
Yeah.
This is called as a molar conductance. Any doubt? Ask me right now.
No.
No doubt. That's good.
No.
Now, next topic we are discussing here is equivalent conductance. Equivalent conductance. It is denoted by lambda EQ. Equivalent conductance. Okay.
Okay.
It is the conductance due to all ions produced from 1 gram equivalent of solute of electrolyte. Present between two electrodes separated by 1 centimeter and area of cross section is so large that whole of the solution is contained between the two electrodes. right? Do you find any difference between the previous definition and this definition? Do you find some difference?
It's 1 gram of equivalent electrolyte. So in the old one, you used you used 1 mole. Now you're using 1 gram.
Yeah, 1 gram equivalent.
What do you mean by equal?
Yeah, I will tell you. In case, okay, I will discuss what is the meaning of 1 gram equivalent. 1 gram equivalent of electrolyte is equal to molecular mass upon total charge on cation. Suppose I say I have NaCl, the total molecular mass comes out to be 58.5, but the charge on the cation is equal to +1, so it is a +1 ohm. Suppose here we have a CaCl2, get its molecular mass 111, but divide by 2 because the charge in the cation is +2. So equivalent mass is, gram equivalent is equal to molecular mass upon total charge of the cation. Right?
Okay.
Now, suppose I say I have this electrode here, and I connect it with, and here I have electrolyte in between the two, and these electrolytes is 1 gram equivalent. Right? Now, whatever the conductance will be observed will be equivalent conductance, and that will be equal to the specific conductance because it is in 1 cubic centimeter. Right?
Right.
But if the volume is whole of the 1 gram equivalent cannot be fit into this 1 cubic centimeter, then we can increase the surface area, but the distance should be again kept 1 centimeter. It means the total volume will increase, so multiply with the volume V. Right? Kappa into volume V.
Okay, so when you say that you can increase the cross section, you're like, doesn't the volume change?
Yeah, that's why I'm multiplying with the volume. How much?
Okay, so the volume is the total volume, like including the cross section.
Yes.
Okay.
So you know that you have a normality equation. Normality is equal to number of gram equivalent upon volume in solution.
I don't know that one.
This normality term is not clear to you?
I don't know what normality is. Yeah.
Okay. You know the molarity here?
Yeah, number of moles
upon volume of solution milliliter.
Yeah.
Right? Into 1000. That we have discussed in the last topic also.
Yeah.
So here we have a normality term. Normality is equal to number of gram equivalents upon volume of solution milliliters. And what is gram equivalent? Molecular mass upon charge in the cation.
Oh, okay.
Right. So here we are putting a 1 gram equivalent here. So volume is equal to 1000 upon normality. So multiply by 1000 upon normality is equal to. Is that clear?
Yeah. Yeah.
Any doubt?
And wait, so okay. And where did the gram equivalent come in the normality equation?
This is by the definition. This is
so
by definition.
Okay.
So based upon this, I will be discussing some numericals with you.
Okay.
Yeah, you can try this question. Are you doing it?
So the difference between molar conductance and specific conductance is that molar conductance you have to divide by the molar mass, right? And then, so to get the answer, you just divide the conductance by the molar mass, right? Can you solve it out?
See here, specific conductance of 0.1 molar means molarity is given to you. 0.1 molar. Kappa is given to you. Specific conductance is 1.06 10 to the power minus 2. Ohm inverse, centimeter inverse. Right?
Right.
And its molar conductivity, molar conductance, with lambda m to be determined. And we know the formula, lambda m is equal to kappa into 1000 upon molarity, right? So kappa is given here 1.06 10 to the power minus 2 multiplied by 1000 divided by molarity is 0.1 means 10 to the power minus 1. So it is a 1.06 into 10 to the power minus 2 multiplied by 10 to the power minus 3 here and minus 4 here. Got it? So 1.06 into 10 to the power, it's a plus 2. So plus 2. So option A is the correct answer.
Okay, so the molar mass we got is 10 to the power negative 1 because of the molar solution, right?
Yeah.
Okay. So wait, again, molar solution is moles upon volume. So can you just tell me how you got 0.1 as the molar mass?
I'm not getting you.
How did you get the molar mass, basically?
Not molar mass, it's the molarity here.
Oh, okay.
And molarity is already given to you.
Okay.
Right?
Right, okay.
This question we have done. Okay. Dilution we have not done. Wait. Okay, this thing you can do. This question you can do.
Is it number 3?
It is the second option correct answer.
So So is there heat generated in electrolytic conduction?
Yes, whenever we have a conduction of any type, whether it is electrolytic or electronic, heat is generated. Whether it is a metallic conductance or it is a electrolytic conductance, heat is generated.
Okay.
Right, you have seen that your all electronic devices or electrical devices, they get heated up.
Yeah.
Right? And in the batteries also, wherever we have batteries, the batteries also get heated up. So there the electrolytes are working.
Okay. Because I keep thinking that electrolytic conduction is in a solution. Is it not necessarily in a solution?
Not necessarily. This thing I have not discussed. Wait a minute. This thing I have not discussed yet. Can you complete it fast?
A. Number option B. Option number B.
B 1 4 7. Yeah, you're right. Are you solving it?
Yeah. I'm getting like B and D to be 6 plus. Is the answer B?
Answer is C.
Oh, has the least. Okay. That was, yeah.
In case of the C, the plus 2.
Yeah, no, I thought I was looking for the highest. Never mind. A. Hello? Option A. B.
For the 2 hydrogens, right? For the carbon is putting an X and minus 2 for the oxygen, minus 2 into 2 is 4. So X comes out to be equal to 2.
Oxygen is 2?
Oxygen is minus 2. Oxygen is generally minus 2.
Oh, I thought it was minus 1.
No. Minus 1 is only in case of peroxides.
Okay.
Can you calculate this one?
B. Option B.
Absolutely. Now the next topic. Right.
Okay.
Topic is now electrolysis. Can I have something about electrolysis?
Is it? Not sure.
Okay. What we do, we take up sodium chloride and melt it. Right? You will get here sodium ions and chloride, right? And you take up a beaker, and in this beaker we have a sodium and a chloride. And now we pass current here. One terminal is negative and the positive here. Towards this negative sodium ion move, and towards the positive the negative ion move, right?
Yeah.
So this is the cathode. Negative is cathode and positive is anode, right?
Yeah.
So at anode, what will happen? These chloride ions will lose electron, and two such chlorine atoms will combine to form Cl2.
Yeah.
Right? to form Cl2. So it means here chlorine gas will be liberated here.
Yeah.
And at cathode, sodium ion will be attracted. They will gain electron and become sodium atom. It means sodium metal will be deposited over here. This whole phenomena is called as electrolysis. This whole phenomena is called as electrolysis.
Okay.
Right. It means the phenomena of electrolysis. We can say it is phenomena of passage of current in molten or aqueous electrolyte. Right? It's a phenomenon of passage of molten or aqueous electrolyte accompanied by reduction and oxidation. You can see that the loss of electron is called oxidation and gain of electron is called as reduction. And production of substances at cathode and anode. Right? At cathode and anode. The whole phenomena is called as electrolysis.
Okay.
So this electrolysis is basically a phenomena in which you pass the current in the molten or aqueous electrolyte, which undergoes either oxidation and reduction at cathode and anode and produce substances. Means here we are getting the chlorine gas and here we are getting the sodium metal. Right? The whole phenomena is called as a electrolysis.
Okay.
Any doubt?
No.
No. Now, this electrolysis is of two types. We will discuss electrolysis in two different categories here. One will discuss here qualitative.
Okay.
Other will discuss here quantitative. In the qualitative, we will discuss what products will be formed at cathode and anode. And in quantitative, we will discuss about how much it will be produced.
Okay.
Right? How much it will be produced. So,
okay.
In the qualitative part, first of all discussing here what are those factors which will be affecting the product formation at cathode and anode. Right? What are those factors which affect the product formation at cathode and anode?
That's quantitative.
Qualitative. And in quantitative, we'll discuss about how much it will be produced.
Okay.
Right.
Okay.
So I'll discuss about those factors first. The factors are: number one, nature of electrolyte. Number two is nature of electrode. Number three is concentration. Of electrolyte. And number four is the current density. And number five is use of same metal electrode as present in the solution. As present in solution, right?
Yeah, okay.
Getting me?
Yeah.
Okay, now I'll discuss all this in detail, one by one. So first of all, I'll discuss about the nature of electrolyte. Here we have chosen here sodium chloride, that is molten, and we are using here platinum, that is inert electrode, right?
Yeah.
The point here is we are using here molten, and the other case I'll discuss here the NaCl as an aqueous using platinum electrode. It means by using the aqueous means when dissolved in water, and molten means when it is the molten state, means if we have heated it and brought to the melt form, molten form.
Okay.
The product formed in the two cases are different. Product formation in the two cases are different here, right? What is the difference? Let us see here. In case of the molten, we have already discussed that this will give here sodium positive and chloride negative, and at cathode is negative, right? The positive will be attracted and sodium will be formed here. But at anode, these chlorides will give electrons, right? And two such chlorine atom will combine to form Cl2. It means you are getting a sodium and a chlorine here, right? At anode chlorine and at cathode sodium. And now I'll tell you what will happen if you are using here aqueous, right? So do you have any doubt till now?
No.
So I'll discuss now in the aqueous phase. Aqueous phase means it is not dissolved in water. So it will dissociate to form here Na positive and Cl negative ion, and water dissociate here H positive and OH negative ion. And here we have a beaker which contains all these ions. Getting me?
Yeah.
Right. So, first of all we go to the cathode. Cathode means the negative terminal, anode is positive terminal. At cathode, H positive and Na positive both may be attracted, right? Both may be attracted. So H positive can gain one electron to become H atom, and two such H atom combine to form here H2 gas. Right? So sodium positive may can gain one electron, become sodium atom here. Getting me?
Yeah.
So either one of the two processes will take place, not of the two. Not both will not take place. Either it is a hydrogen gas produced or sodium will be produced.
Okay.
This will depend upon the reduction potential. We know that reduction potential of hydrogen is equal to 0. And reduction potential of sodium is equal to how much? Can you tell me? Minus 1.37. It is in the electrochemical series.
Okay.
Which has a higher value? Hydrogen has a higher value. The one which has a higher reduction potential will undergo reduction. It means the H2 gas will be produced, not the sodium. Sodium will not be produced. At cathode, hydrogen will be produced, but sodium will not be produced. So we can say from here the H2 gas will be liberated here. Getting me?
Yeah.
Okay. And now we go to anode now. At anode, what will happen? Chloride ion and the OH ion both will be attracted. If the chloride ion is discharged, I am using a word discharged, charge is getting over. So 2 chlorine will combine to form here Cl2 gas. Right?
Yeah.
And at cathode, at cathode, either this or it may be OH ion may be discharged. So upon balancing, it comes out to be like this.
Okay.
So O2 gas will be liberated. Either one or two will take place, right? So
yeah, and you figure which, but
which one? Now we have to discuss what will take place. Either chloride will be discharged or OH ion will be discharged. And for that we have a term here. First of all, discuss that term. Discharge potential. Discharge potential. Discharge potential means the potential required to, the voltage required to discharge an ion. How much potential, how much voltage is required to discharge a particular ion? For that you have to remember one sequence here. Maximum potential is required to discharge the sulphate. Right?
Right.
Maximum is required to discharge the sulphate ion. And after that, it's a nitrate ion. Then it is a chloride ion. Just a minute. Fluoride ion, chloride ion, OH ion, fluoride ion, all these are required. So if you compare a chlorine and the OH ion, which require, just a minute. Here it is a OH ion, not here. Then bromide ion, last the iodide ion. So if you compare the OH and the Cl, which will be discharged first? The one which will require less amount of energy, right?
Yeah.
So which require less amount of energy. Less potential is required by the chloride ion. So this will take place, this will not take place. Right?
Okay. Yeah.
One or two will take place, both will not take place. It means the chloride ion will be discharged.
Yeah.
The oxygen gas will not be liberated. So we say at cathode it is a hydrogen gas produced and at anode the chlorine gas is liberated. Is it different from that in the molten state?
Little bit.
What is the difference there?
The anion gets collected at the cathode, and the cation gets collected at the anode.
Mm-hmm.
But here,
what is the difference in the product? At cathode, what is the produced in the molten state? In the molten at cathode, what is produced?
CO minus.
Check it out. Have you noted down?
Yeah.
Check there.
It's CO minus, right?
No, sodium is produced there. See it there. At cathode, sodium is produced. Cathode,
Wait,
I'm talking about the cathode. And at anode, chlorine is liberated.
Oh, okay.
But here, in the aqueous state, at cathode, it is the hydrogen, and at anode, it is the chloride.
Oh, okay. Okay.
Now, it means there is a difference, right? If it choose molten or aqueous, the product will be different.
Yeah.
No, wait a minute. Thanks for this question. I'll tell you that brine solution is a 28% NaCl solution. Brine solution is a 28% sodium chloride.
Is it number 1?
Yes, you are right. Okay. Now let's choose
Is it number 1 again?
Yeah, you're right. Think about this question now.
The cathode is negative, right?
Yeah.
Number 3?
No. 4. There will be no net movement.
Oh. Number 3?
Right, you're right.
Huh?
Yes, tell me, what is the answer?
Nothing, I heard a background voice. Number 1.
Number 1?
Number 1?
No.
Yeah.
No.
Hydroxyl.
Hydroxyl is...
OH negative ion. I'll tell you how.
Okay.
Sulfuric acid is H2SO4, right?
Yeah.
So it dissociates to give 2H ions and sulfate ion. And water, aqueous solution. So it forms here H positive ions and OH negative ion. So at anode, these two ions will be discharged. And now I told you about the discharge potential, which has lower discharge potential, OH ions or sulfate ions.
I'm not sure.
I gave the sequence right now. On the time.
Oh.
See that sequence?
I don't think I wrote down the sequence.
Have you not counted down?
No.
You must note down everything. Maximum for the sulfate ion, then nitrate ion, then OH ion, then we have a fluoride ion, then chloride ion, then bromide ion, then iodide ion. So out to the sulfate and the OH ion, which require less discharge potential.
Sulfate?
OH, less discharge potential.
Oh, okay.
Which is required. So that will be discharged first. Getting me?
Hydroxyl is OH? I thought that was...
Yeah, OH negative ion. OH negative ion. OH ion is the discharge potential.
I thought OH minus was hydroxide.
No. Hydroxide is OH negative. Hydroxyl is the same thing. Basically, hydroxyl or hydroxide ion is the same thing.
Okay. Is it number 1?
No. Okay, I just get that. Yes. we are discussing about the electrolysis, right? And talked about the nature of electrolyte. Now we discuss about concentration of electrolyte. If we change the concentration, how will it affect? In my previous case, I have discussed here aqueous NaCl, but that is a concentrated NaCl using platinum electrode, right? And there we found that at cathode, what do we find? What do you find here? H2.
Yeah.
And at anode, it is Cl2. Right? That is the case, that is the result of the previous one. And now, what we do, we dilute it. Dilute NaCl, aqueous, using platinum electrode. If I dilute it now, dilute means they are adding more water, right? We have now excess of the water here. We have NaCl, we have water, but water is in more quantity. So it produces here Na positive, Cl negative. It gives here H positive and OH negative ion. Right?
Yeah.
Now, when we pass current here, I am passing current here. It's negative, it's a positive. Towards the negative, H positive and Na positive both are moving.
Yeah.
But Na positive is very, very less in amount. And, and moreover, hydrogen has a higher reduction potential. Reduction potential of hydrogen, I told you it is 0. And the reduction potential of the Na positive is minus 1.37 volt. So this will take place, this will not take place. It means here you will get the hydrogen gas, not a problem at all. But in the at the anode, Cl negative is a very, very less amount because the solution dilute. So OH ion will move and get discharged. So the OH ion will be discharged to H2O, oxygen, and electrons, 4 electrons. So the oxygen gas will be liberated here. So O2 gas will be liberated here. Getting me? Because Cl negative ions are not present in large quantity. They are in very, very less quantity.
So is that LiOH over there?
OH ion will be discharged.
Oh, so is that you wrote something like next to the OH minus? What is that?
Yes.
What did you write next? Is that chlorine? What did you write over there? Like next to the OH minus?
I'm not getting you.
No, in the equation, right, for OH, like next to the beaker.
4 OH ion.
Oh, okay, it's 4. Okay.
In and out.
No.
Right. So this is the effect of concentration. That in dilute we get here hydrogen and chlorine, whereas in case of concentrated we get the hydrogen and oxygen. You getting me? At cathode it is the hydrogen and at anode it is the oxygen. Difference is there. It means if we change the concentration, If we change the concentration, what will happen? Different productive form. Right?
Yeah.
Here we get the hydrogen gas and here we get the oxygen gas. Hydrogen here. But here we get a chlorine and here we get the oxygen. Are you getting me?
Yeah.
Note down each and every point and revise it again and again. Because it's a very, very important question for you.
Okay.
And now I discuss the nature of electrodes. Till now I have been using here platinum electrodes. Now I will be using here some reactive element here. Sodium chloride, aqueous, dilute, using mercury as cathode. Using mercury as cathode. What is the physical form of the mercury?
Hg.
What is the physical form?
Huh?
What is the physical form of mercury? Physical state of mercury?
A liquid.
Liquid, right?
Yeah.
Right. So, can we make its electrode? No. Yeah, we can't make it electrode. So what we'll be doing is, we keep the mercury at the bottom. This is the mercury here. And make it cathode, negative. And make a anode here or the platinum. Hello?
Yeah, you make...
We can't make an electrode, standing electrode or suspended electron on the mercury. So it's at the bottom of the container, right? And in between we have here sodium positive and Cl negative ion, H positive and OH negative ion. So first of all we see towards the cathode what will happen. At cathode both can get reduced, sodium as well as the hydrogen. What do you expect which should get reduced?
Sodium.
Why?
It has the lower potential.
No.
Is it hydrogen?
No. Yeah, hydrogen has higher potential, right? So we are expecting here that hydrogen should be produced and hydrogen should get reduced here. Hydrogen should get reduced here, but actually it does not happen. It is sodium that get reduced. Because the sodium here get dissolved in mercury and form here NaHgX. It is a amalgam is formed. Sodium mercury amalgam is formed. Sodium mercury amalgam is formed, right? So this sodium mercury amalgam react with water and produce here NaOH plus hydrogen gas and mercury. Again the product is hydrogen what we are expecting, but what get reduced is the sodium, which will be discharged sodium. What will be produced? Hydrogen gas. The two things are different. Getting me?
Yeah.
Now at anode. At anode we have a chloride ion and OH ion. Which will be discharged first, you tell me? Toward this, which will be discharged here?
The chloride.
So this will be discharged and chlorine gas will be liberated.
Okay, so basically you put liquid mercury in a beaker with water and then you set up a platinum electrode and Is this what happens?
Yes, you are absolutely right. Only thing is now mercury is reactive here. It'll tend to dissolve the sodium into it.
Okay.
So the product will be different in the two cases.
Okay.
Getting me?
Yeah.
Next I'm talking about current density.
Okay.
Current density. We have two types of current density. One is called as a high current density. And we have a low current density. Right? If the voltage is above 220 volt, then we say it's a high current density. If the voltage is less than 220 volt, we call it low current density. Right? Getting me?
Yeah.
First of all, I had defined what is meant by the high current density and the low current density.
Yeah.
So we'll see here that we are using here electrolysis of H2SO4 aqueous solution at high current density, and then we'll talk about it low current density. First of all, I'm discussing here at the high current density. At the high current density, the sulfuric acid dissociate to give H positive plus HSO4 negative ion, and water dissociate to give here H positive plus OH negative ion. So at cathode, what will happen? We don't have any competition here. Both are hydrogens here.
Yeah.
Right? Both are hydrogen here. So the two H positive ion gain 2 electron and become H2 gas. Got it?
Where are those 2 electrons coming from?
Now the HSO4 negative ion loses electron, and two such HSO4 give 2 electrons, and they form a H2S2O8, and the electron lost by this one is gained by this one.
Okay.
And this compound is called as a peroxodisulfuric acid. This is called as a peroxodisulfuric acid. Getting me?
Yeah.
Right. And now talk about the low current density. At low current density, this sulfuric acid dissociates to give 2H positive plus sulphate ion, and water dissociates to give H positive plus OH negative ion. Right?
Okay.
Now, at cathode, there is no competition, both are giving the H positive ion. So they will give you a 2H atom, and finally they will give the H2 gas. Are you getting it?
Wait, so at the cathode there's 2 H plus and
the reduction. At cathode, reduction takes place.
oh, okay.
And at anode we have 2 ions, one is sulphate ion and the OH ion. Which will be discharged first?
The OH, right?
Yeah, OH ion. So the OH ion get discharged to give water, oxygen and 4 electrons. Are you getting me?
So 4OH becomes 2 water plus O2 plus 4. Like.
Yeah.
So is the OH minus getting reduced?
Getting oxidized.
Oh, it's losing electrons. Okay.
Yeah.
Okay.
So you can see the difference in the product formation here. At anode, here we are getting the peroxidized sulfuric acid, and here we are getting the oxygen gas.
Yeah.
And here we are getting the hydrogen gas. Here also we are getting the hydrogen gas. Same similarity here.
Oh, okay.
We find any problem here.
So I'm just trying to understand what happened in the second step.
Let's go for it. Tell me if you find any problem.
So in the higher current density, at the anode it was the HSO4 that got oxidized, but in low current density it's the hydroxide that got oxidized.
Getting me?
Yeah. I just don't understand why. Like, what is the reason for the change at the anode?
Yeah. You can see that this is completely dissociated here. But here we have an HSO4 and H positive ion. At a high current density and a low current density, the dissociation is different. In case of the high current density, it is not completely dissociated. It gives only one H positive ion and then HSO4 negative ion. Whereas in case of the low current density, it undergoes complete dissociation to give 2 H positive ion and 1 sulfate ion.
Okay, so should we remember that at high current density, it doesn't dissociate completely, and at low it does?
Yes, you have to remember this thing.
Okay.
Then we can proceed ahead with logic.
Okay.
And now discuss about the last factor that affect the product formation here. That is.
So 1 minute.
Yes, please.
So 1 minute. Be right back. Just give me a minute.
Okay.
Okay, let's start.
Okay. Now what we are doing is we are using the same metal electrode which are present in the solution. It's a beaker. It contains aqueous copper sulfate. Aqueous is when dissolved in water. Right? Can you tell me which metal is here inside the electrode?
Copper.
Copper, right. So what I do is I take up here electrodes made up of copper only.
Okay, you're not using like platinum, right?
Yeah, I'm using the same metal electrode. You can see I'm using the word same.
Yeah.
So this is a negative terminal at the positive terminal. At the cathode is negative, right? The copper ion and the H positive ion both will be attracted. So the reduction potential of copper is positive 0.34 volt, right? And the reduction potential of hydrogen is 0. Can you tell me out of these two which is having higher value?
Which is having what?
Higher value, which is a higher reduction potential value.
The copper.
Right. So the copper will be reduced. It means the copper ion will be going over here and the copper will be deposited over here. Right? So copper will be deposited here. This is at cathode. Now at anode, what will happen? At anode we have possibility that sulphate ion may be discharged or OH ion may be discharged. Out of these two, which is a lower discharge potential? Can you tell me?
Hydroxide.
Yeah. It means one possibility is it may undergo oxidation and produce air oxygen. Right?
Yeah.
And other possibility is, for more possibilities also there, copper itself undergoes oxidation. The copper comes into the solution as the copper ions.
Okay.
Right? Out of these two, this takes place, this requires less potential. This will not take place. So I am saying here, whenever we use the same metal electrode, at anode, the metal itself undergoes oxidation, but not the OH ions. So what will happen slowly and slowly, the copper will be completely dissolved over here, and the copper coming from here will be reduced over here. So after some time, what will happen here? This cathode will become thick, but anode will become thin, and if there is any impurity here, it will settle down here. If there is any impurity at the anode part, that will settle down, and we call it as a anode mud.
Okay.
Right? And slowly this will even disappear. Means the anodic copper will completely disappear. Are you getting me?
Yeah.
So it means if we have an impure copper, if you impure copper here, then we can make it anode, and a pure copper can be made cathode. To purify the impurity, we can use it like this. The pure copper will go over the pure copper, and the impurity will settle down, and anode mud will be formed.
Okay.
This is the application of the electrolysis.
Okay. Okay, this topic, it's not like I don't so one thing I have a doubt is, these membrane potentials, right? Or no, these, the potential of the electrodes, how do you, remember them, or?
Okay, our next topic is our electrochemical cell, right? So some values you will remember there, by logic you will remember all there, but for this topic you have to remember it. Right? It will more clear. It will more clear in my next topic.
Okay.
So I think that the concept is clear. You have to remember things, right?
Yeah. Yeah. Number 4.
Maximum conductivity here. because that contains more number of ions, right?
Yeah, there's no such thing as conductivity water, right?
No, nothing.
Okay. Is it 4?
Yeah, that gives more number of ions.
Yeah.
This I have not discussed with you.
Yeah.
Leave it for this. I have not discussed this. Yeah.
Is it 1?
Yeah. Is that clear?
I'm not sure why 3 and 4 are wrong though.
Okay. Here we have zinc nitrate. Zinc nitrate is a NZnNO3 that will form a zinc 2 positive and NO3 negative ion, right?
Right.
Aqueous medium means water is H positive plus OH negative ion. And now we are passing current here. So at cathode, out of the zinc and hydrogen, which is a higher potential, remember here the zinc value for the timing, remember it is minus 0.76 volt, and that of hydrogen now you have remembered already 0.00 volt. Can you tell me which will be reduced now?
Zinc?
No, hydrogen, because that is a higher potential.
Wait, I thought you were supposed to look for lower potential.
No, the one which has a higher potential, which has a higher reduction potential will be reduced. But at the same time, you are right, but at anode, out of these two, which will require less potential, here we are talking about the discharge potential. So the OH ion will be discharged first, you know that sequence. At cathode you have to see the reduction potential, and at anode you have to see the discharge potential.
Oh, okay.
Right? It means it will be remaining in the solution only. It will not it leaks out, not it will not produce. So first option the correct answer, right?
Right.
Here we can say hydrogen at the hydrogen gas will be produced and evolved at anode, that is wrong, that is the cathode. Oxygen is evolved and at anode, yes, D is the correct answer, not this one even.
Okay.
So oxygen gas is evolved at anode, right?
Right.
So go through all this and see you next week same time in the on Saturday, right?
Yeah. So this chapter that we're doing, what's it called again?
Pardon, I'm not getting you.
What is this chapter called again?
Electrochemistry.
Okay. That's in the end of the book somewhere, right?
You see it there in your book, right?
I'll check, yeah.
Okay then.
Yeah. Okay, see you.